Hello, everyone. Today's video, we're going to be diving into the second part of Unit 3, which is all revolving around a specific area called nuclear chemistry. And this usually makes a lot of my students incredibly nervous because it sounds like rocket science and super advanced information, and we're only at the beginning of the school year. But the term nuclear is in close relation to nucleus. So all nuclear chemistry is the chemistry specifically of the nucleus of an atom, which we already know everything about the nucleus of an atom. So it's really nothing new. We're just talking about what happens if we were to go in and change up the makeup of a nucleus. Okay. These two terms on your screen are probably something that you've heard of before. And so in terms of like nuclear energy and nuclear power, there are two major energy producing reactions, and that is fission and fusion. And so fission starts with an I, and that is the splitting of an atom's nucleus. All right, if you think of like during an earthquake, the ground sometimes will open up and it's called a fissure. We're taking an atom's nucleus and we're trying to split it. And so during fission, a tremendous amount of energy is released. And this is the common practice that's used in a lot of nuclear power plants across the world. They take a really large radioactive atom, like over here we've got a radioactive sample of uranium-235, and they imply some kind of an initial amount of energy, and they cause that atom to split, and tons of energy gets released, which then is transferred through the appropriate channels to turn that into power, to turn it into electricity. There's actually quite a few nuclear power plants in the state of Illinois that are currently powering the city of Chicago, right? So fission reactions are profitable because they can continue in a process known as a chain reaction. Right, so we'll see that how that plays out here in just a second. Okay, the second reaction that we're going to talk about on this page is called fusion. And fusion is essentially the opposite of fission. It's when you take two smaller nuclei and you fuse them together. You combine them into one larger nucleus. And this process actually produces more energy than a fission reaction because we're overcoming the initial nuclear stability of the smaller atoms and we're forcing them into one larger nucleus. The downside of this is that it takes a lot of energy to get that to happen, and fusion reactions aren't easily continuous. So this process hasn't been harnessed yet by us in a nuclear power plant, but it does occur all the time in every sun and star within the outer space. So every time two hydrogen atoms fuse together in our sun, it produces a new helium atom, and then tons of energy gets released, and it's radiating out all across the galaxy. Right? So I want to spend a little bit of time over here on the right with this image and document what we're looking at in terms of this fission reaction. So if we write down below, we've started with this uranium-235 atom. And so we know that the bottom left number tells us that this particular nucleus has 92 protons and a large number of neutrons, because 235 is the total protons plus neutrons. And what they start a fission reaction with is just by shooting one neutron into that nucleus. So a neutron is, in the wrong spot. A neutron does not have any protons, because it's just one subatomic particle. But again, that mass number is protons plus neutrons. So there's at least one neutron accounted for. So it's 1, 0. And we're going to add that to this uranium-235. And it causes this dimpling to occur because we're taking something that's already kind of unstable, a radioactive atom, and we're breaking that stability or instability. And then the top half will split off and form one atom and a different atom. And then there's these other kind of shotgun effect released neutrons that get scattered out throughout the container that the reaction's occurring. So this uranium-235 is what's going into the reaction. And so we draw it always to the left of an arrow. And what comes out of that reaction, we draw on the right side of the arrow. So we produce one atom here, which is strontium-90. And again, we know that because it's the element strontium, its atomic number is 38 on the periodic table, so halfway down in group 2. And the other atom that gets produced is another smaller atom. This time it's Xe, that's xenon. It has an atomic number of 54 and a mass number of 143. And then we've got 1, 2, 3 additional neutrons that are released. Now, while this number-letter reaction scheme that I wrote out on the board in red looks really complicated, it's actually a really simple math equation. Right? If we just focus on the bottom half of those numbers, we're saying 0 plus 92 protons equals 38 plus 54 plus 0 protons. Well, 38 plus 54 equals 92. So it's just our way of doing a little bit of accounting. The uranium atom brought in 92 protons, and those 92 protons have split up. 38 went to make this strontium atom, and 54 went to make this xenon atom. Okay? So the same accounting can be done for the top row, which is just the mass numbers of each of those isotopes. 1 neutron plus 235 protons of neutrons equals 236. And over on this side, we had 90 plus 143 plus the 3 neutrons that were released. And this total on the right, 90 plus 143 plus 3 equals 236. That was originally combined in on the reaction side. And so all this, again, is simply saying, are all of the protons and neutrons that were in the initial components of the reaction still accounted for? And they have to all equal up. They have to still be accounted for. Okay. So we talked about how fission was a chain reaction. Here we see this initial neutron coming in, and it's going to split that atom. But then as a byproduct, another neutron shoots off from that splitting because they're really large nuclei that are breaking up into tinier pieces. And then this neutron hits this atom, splits it, hits this atom, and splits it. And then those 2 byproducts shoot off their own nuclei and then split these 4 atoms. And within a matter of time, everything is splitting in a nearby uranium atom, causing a bunch of extra neutrons to fire off. And it's just propagating and continuing that fission to occur just from one small input of energy. And so we're able to keep that reaction continuous until we put in a nuclear power plant to use what's called a control rod, and they actually remove the control rod, which is the uranium source, to slow the chain reaction down to eventually stop it from producing too much power. Because they learned kind of the hard way in the Russian power plants, Chernobyl, that too much power can lead to some pretty devastating results. Okay? Down here, we've got a nice visual of a fusion reaction. It's a little bit cleaner to see. We've got these 2 smaller nuclei, a hydrogen and another hydrogen. Again, this is the process that's occurring in our sun right now. Okay, and so we take the 2 smaller nuclei. We've got hydrogen 3 and hydrogen 2. 1 proton each, but one isotope is a little bit heavier than the other. And we're going to combine them together to create one larger nuclei, this 4-2 helium atom, and then 1 extra neutron in this particular fusion reaction. Now that 1 byproduct produced neutron isn't really enough energy to then cause another set of hydrogen atoms to fuse together. So again, the fusion process doesn't really lend itself to some kind of a chain reaction. But hopefully we can still see that that mathematical pattern holds true. We combine together 2, oops, I didn't write a 2 there. We combined together 2 protons and made a helium atom, which has 2 protons in its nucleus. So 1 plus 1 equals 2 plus 0. And then in the top row, the mass numbers are also accounted for. 3 plus 2 equals 5, which equals 4 plus 1. Okay? So again, throughout all of these chemical reactions, the law of conservation of matter still holds very much true. The total number of protons and neutrons that combine or break apart have to equal each other in the end. Okay? And so we've got these other nuclear decay reactions, which we're going to outline on the second page. But a nuclear decay reaction is when an unstable nucleus releases a bunch of energy. And the term that oftentimes gets utilized to talk about energy is radiation. And so radiation gets a really bad reputation because they think it's the cancer-causing source, radioactive material. But the term radiation, or to radiate, is when something releases away from a center. So if you were to stand outside on a sunny day, the heat from the sun is radiating away from the sun. If you're sitting in the LMC right now, listening to this video, the lights in the LMC are radiating away from the bulb. So there's radiation all around you. It's just some of the radiation is bad, what we call ionizing radiation, and some of the radiation is perfectly fine. Sound radiates away from speakers, right? So the larger a nucleus is, the more likely it is to be unstable, and the particles or energy that are released are called radiation. Okay, so all unstable nuclei become more stable by either undergoing nuclear decay, which we're going to outline the types of nuclear decay next, or by releasing energy. And that's pretty common for all radioactive material. It's radiating energy away from its core, trying to stabilize itself. But sometimes as that energy is radiating away, there's a ton of different types of decays that can occur. Okay, so there are 4 major types of decay that we're going to outline here. And we're going to look at them in terms of increasing damage to cellular tissue, or increasing ionizing damage. And the first one, which we call alpha decay, alpha being the first letter in the Greek alphabet, is the least damaging. This is the simple kind of puny radiation that a lot of radioactive material undergoes. And so an alpha particle is a positively charged atom that is made up of 2 protons and 2 neutrons. And quite simply, it's just a helium atom. So right here, that represents an alpha particle. So again, we've got the bottom left number, 2 protons, and the top left number is both 2 protons and 2 neutrons together, adding up to 4. Okay, so for this example, for this alpha decay reaction, we've got a uranium-240 isotope, and 1 alpha particle is being pulled off of it. And so on the right side of the equation, we've got what's left over plus the alpha particle that was removed. Okay, so it's kind of like saying this is the sum of the parts all on the left side. Again, we look at this as a math equation. 92 equals 90 plus 2. That's true. 240 equals 236 plus 4. Also true. So this nuclear reaction is balanced, and all protons and neutrons are accounted for. Okay. In terms of ionizing damage, alpha decay is the least damaging. Right? It turns into a helium atom. That's the stuff that you fill party balloons with. So there's not a lot of damage incurred from alpha decay. It's so not damaging that it's easily blocked by a sheet of paper. And most comforting is that it's easily blocked by your skin. Alpha decay doesn't easily get absorbed through your skin. Okay? So if you look off to the right, we've got another example of an alpha decay reaction. We're starting with this plutonium isotope. It's got 94 protons and 240 for its mass number. And what's happening is that 1 alpha particle is leaving. And we're figuring out what we're left with is this slightly more stable uranium isotope that's got 92 protons and a mass number of 236. Again, we want to make sure 94 equals 2 plus 92. That's correct. 240 equals 4 plus 236. So this leads us to being able to figure out either by the numbers what type of decay is occurring, like what piece would be released, or if we know that an alpha decay is occurring, what is the chemical makeup of the product side, or what's produced as a result of that decay, something that we refer to as the daughter nuclide. Right? All right, the next type of decay we're going to talk about is a beta decay reaction. And instead of an alpha particle, this produces a beta particle, which is a charged electron emitted during radioactive decay. And it's important to know that this can be absorbed or released. We're going to talk about the difference between those two. If we're talking about something decaying, we're talking about something breaking apart. So for this one, we're going to be looking at a beta particle being released. And so this here is our symbol for how we're going to draw a beta particle. It's an electron. Electrons are negatively charged. So we're going to say that for the atomic number, it's a -1. And the mass, because it is not made up of protons or neutrons, it's just an electron. The top left number, the mass number, is always going to be a 0. Okay? So this one has a little bit of a curveball in it because it involves a negative, but the math still holds true. 35 equals 36 minus 1. True. 80 equals 80 plus 0. Also true. So with this, there's a little bit of a chemical conversion here. We take a neutron and actually convert it into a proton. There's like a chemical shift in the way that the subatomic particles are going to behave. Right? In terms of ionizing damage, anytime electrons are released, this is slightly more damaging. All right, so this has the potential to be absorbed by your skin, or most damaging is to be inhaled, and then it could get into your lung tissue and cause some pretty severe damage there, depending on how much you're exposed to. But this stuff still can be blocked, but it would have to be blocked by something slightly thicker than a sheet of paper. This could be blocked by at least a piece of metal. So we're going to say like a sheet of aluminum foil. Does a good job of at least blocking out the penetrating power of beta decay. Right? So if we look over here in the example to the right, we've got this large unstable cesium isotope. It has a mass number of 137. And we know that one electron, there's like these little trail lines here, one electron is emitting, is decaying away from that nucleus. So we produce at least one electron. And then what's left over, well, even if we didn't have this info over here, we know that 137 equals 0 plus 137, and 55 equals -1 plus 56. So the numbers alone tell us what would complete that nuclear decay reaction. And then if we look at the periodic table, we find element 56, and we could say that that has to be an isotope of Ba or barium. Okay, again, that atomic number in the bottom left corner helps you identify the element that is part of the reaction. Okay. The last type, oops, here we go, smart part. The last type of decay that we're going to talk about in terms of releasing is called gamma decay. These are oftentimes referred to as gamma rays, kind of like Bruce Banner exposed himself to a bunch of gamma rays and then turned into the Incredible Hulk. That is definitely not true. If you got the same dosage that Bruce took in the comic, you would not be standing here today. But a gamma ray is essentially just a really high energy source of light that's being released by an unstable radioactive nucleus. So it's a high energy photon, which is a light particle that's emitted by a nucleus during fission, and oftentimes just in any general decay reaction, like alpha or beta decay. It's important that because it is light, to know that it's not made up of matter, which is why it is so incredibly damaging. So it is the most dangerous, the most penetrating form of radiation, and this has to be blocked by at least 6 inches of lead, a really dense heavy metal, or 6 feet of concrete. Right? You don't want to mess with this stuff. This stuff can really do some pretty serious damage to your cellular tissue. Okay? Now, a gamma particle, since it doesn't have any matter, it's not made up of protons, and it's not made up of neutrons or electrons. So the symbol for a gamma particle is the Greek letter for gamma, which I always say is simply drawn like an upside down fish. And then the symbol is 0 mass number, 0 atomic number. So the way that that reaction plays out, pretty simply, here we've got this radioactive plutonium atom, and it's plutonium-240. And they put a little asterisk there to indicate that that starting point is at a higher amount of energy. And then afterwards, a gamma particle or gamma rays are released. And again, the math still has to hold true. 94 equals 0 plus, well, that would have to stay 94. And 240 equals 0 plus, again, 240. So if the only decay that's occurring is gamma decay, the makeup of the atom doesn't really change. It just goes from this higher energy state, indicated by an asterisk, to a lower energy state, indicated without an asterisk. Again, it's just radioactive energy leaving the nucleus to try and stabilize that already unstable nucleus. Okay. The last one we're going to talk about is just a recap for the beta decay, but this time it's called a beta absorption or electron capture. And so this is a type of reaction that is used to try and capture free radioactive beta particles that are released during a radioactive process. And again, this beta particle charged electron, here we're going to be talking about it being absorbed by a nucleus. And in this example, we've got another bromine atom. This time we're adding the beta particle to it. And so the math, again, hopefully you picked up on that pattern, still holds true. 35 minus 1 equals 34, and 80 plus 0 equals 80. So before, in step number 2, our beta particle caused the atom to increase in atomic number. Here, we're absorbing an electron, adding it to the initial bromine atom, and we're decreasing in atomic number. So we go from a bromine atom to a selenium atom. Okay, still the same level of damage because it's a beta particle that's being involved, still could be blocked by aluminum foil, but this time we're adding it into the initial component instead of releasing it as a product of the other reaction.